This is Taylor Williams, and I'll be presenting the scheduled task design pattern. So the intent of the scheduled task design pattern is first knowing what the pattern is about. So the scheduled task pattern is a type of software design pattern that uses real-time systems, and it's not to be confused with the scheduler pattern. A user can create a task scheduler relying on the current time of their system, and overall, the pattern ensures that desired operations are performed at certain points in the future. So the motivation. So real-time systems find it necessary to have tasks done at specific times, and implementing a system using a scheduled task pattern is one of the simplest approaches in doing so. So in comparison, with the schedule pattern, the schedule pattern would delay access to a resource until absolutely necessary, whereas with the scheduled task pattern, a task execution is delayed until a determined time. So let's start with the structure of the pattern itself. So real-time scheduled tasks mainly consists of three parts: the task itself, the jobs that schedule the tasks, so when the task will run and how long it will run, and the job registry that executes the task, so the method that would actually run the task itself. And usually systems like this using the scheduled task pattern are implemented using cron on Linux servers, but you can also do this through Java or Python. It is pretty lenient with that. So the common configuration syntax regarding scheduling itself is exactly like this. So you have the minutes. You can schedule tasks to perform within a certain minute or within an hour, the day of the month, or a day of the week. And then all that you put in through a command to execute. So a real-time scheduler is designed to provide a real-time guarantees. So once a task is scheduled at a certain amount of time, if a user wants to run one more task, the scheduler will decide what action to take based on the load it's currently carrying. So it cannot guarantee that a task can continue running at the desired rates, then it will refuse another task being added. So it has tasks at a priority. This mainly applies for when the user wants to run longer tasks, and is associated with the rate monotonic algorithm, a procedure for assigning fixed priorities to tasks, and assign the priority of each task according to its period, so that the shorter the period, the higher the priority. So the shorter the task is, the higher it is on the schedule's priority list. So here is a basic UML diagram for just a task pattern itself. So there's an overall class for the task that contains methods that will actually schedule the task and set the time in which it will run, and the size of the tasks, basically how long the task will run. And the specific tasks itself are extended from the main class, and it overrides the run method that is put into the main class. So each task has its own run method or execution method so that the task can actually perform. So here is a more detailed version of the UML diagram that is also can be used. So with this one, it'll include a interface that displays the commands to the user, and it also would implement a mediator. So the mediator would track the status of all the tasks, informing the user if the task is currently running, if the task was successful at running, or if the task failed at any certain point. So what are the consequences of using a scheduled task pattern? There are some issues that can happen when implementing scheduled task patterns, such as when having tasks running concurrently, so a bunch of tasks at once, and OS can find its processes becoming slower and slower. If you decide to implement a scheduled task pattern using cron, then the users cannot have their cron jobs exposed to the internet. Or not all tasks the user wants done in a given time frame can possibly be achieved, depending on the priority, or if the scheduler implemented can guarantee the task's execution. So what are the known uses for this type of design pattern? Well, for one, there's many applications that use this, and it's very common. So such as apps that set alarms or reminders, or the option to send an email at a specific time, setting a time for your computer or phone to update, restricting screen time on a device, or even using a calendar application to notify user when a date occurs. So anything that has to do with setting something to happen at a certain time, that's when you would commonly use a scheduled task pattern. So here's like a little demo, and with this demo, we can implement using Python. Python has its own schedule library. So that is what's going to be used with this demo. So the main structures of the scheduler itself is already implemented through the library. So this is just to show the basic structure of the pattern itself. So here is the main class for the overall task. So in this case, the task is alarms, and this is the alarm system. So within this alarm class, it has the user's alarms that's already built into it in the function display alarm. And then it has the run method, but this time denoted as execute. And then it has a method for displaying an error if something wrong happens. So here are the classes that would extend the main class alarm system and with the alarm tasks, work, school, and homework. So basically the client or the user has 3 alarms, and these are the 3 alarms itself under different classes named after them, and they're all extended from the main alarm system. So as you can see with class work, it has the execute from the main class, but it shows what the alarm is made of. So the alarm will show the sentence time to go to work, and that alarm itself is scheduled to go off every 20 seconds. And then for the next user alarm, it's school. So that alarm is time to go to school, and that alarm will go off at 15 seconds. And then there's another alarm, homework, that says time to start homework, and that alarm go off every 10 seconds. And this is the main function that would implement the scheduled task system itself. So first, the alarms will display to the user, and then the user is given the option if they want to activate all the alarms or not. And if they activate all the alarms, then it'll direct the user to the execute. So the alarms would be set, and then they would go off to the user itself. Now here is just some screenshots of the output of the demo. So as you can see, it displays the name of the alarm system, and then it'll list off the alarms that the user has already put in there. So work, school, and homework. And then the system will ask if they want to activate their alarms. And in this instance, it's yes. And then slowly, as times for the alarms come on, then it'll denote what the alarm is made of. So the message, the alarm was set. So time to start homework, time to go to school. And as time went by, the alarms kept repeating itself. And of course, this is just the basic implementation of it. If you want to do more on the lines of the advanced one, then you can put a method to stop the task or when to end the task. This is just more of the simple example. And I can also show this in real time as well. So over here, just put in the code of the system. And here you are. So it displayed to user work, school, homework. And does the user want to activate? We'll say yes as again. And then as time goes on, the alarms will appear. The user's alarms will set off one by one. And you can also change this to not be seconds. You can change it to minutes, days, a certain day in a month, as described before. And that is it. And thank you.